Let's talk about electric potential, V. This is confusing. This is one of, if not the most confusing ideas in all of physics. For one, it sounds just like electric potential energy, but it's not. This is different. It's related to electric potential energy, but the electric potential V is different from electric potential energy. So that was a poor choice of naming. And the other reason it's confusing is that the electric potential V is a number. Just a number, that's it, associated with points in space. So it's abstract. This is an abstract idea. You can't go hold electric potential in your hand. It's a number, an abstract number at every point in space. Here's points in space. I just put circles around empty spots on the screen. There's like nothing here. I just put circles here. These are circles around empty points in space, just so we can talk about them explicitly. And, well, if there was no charge around, if you literally had an empty universe, the V value at every point in this universe would be 0. It'd be 0 there, it'd be 0 over here. The number associated with every point in space would be 0. That'd be boring and useless. How do we make it so that the V value, the electric potential value, is not 0? We'll just stick a charge in here. So let's take a big old positive Q at some point in space over here. Take a big old charge and we'll stick it right there. Now, points in space around this charge will have a V value that's non-zero. And they'll be big if you're near this Q. So the V values around here are going to be really big. And then the V values way out here will be smaller. The farther away you go, the smaller it gets. And why do we care? Who cares? The reason we care is this. The units of electric potential are joules per coulomb. So electric potential has units of joules per coulomb. And that gives you a hint of why you should care. We care about joules. Joules are energy. So if something can have energy, that's useful. You can get work out of that, or it can turn into kinetic energy. And joules per coulomb, that lets you know, all right, well, if this point over here happened to have, say, 100 joules per coulomb, let's say the V value at this point in space happened to be 100 joules per coulomb, what that means is, remember, there's nothing there. But if there was something there, if we happened to take, say we had a positive 2 coulomb charge, and we took that charge and we put it there at that empty point in space. Before we put it there, the V value was 100. When we stick it here, who cares? Why do we care about this 100 value? Because, look, it's 100 joules per coulomb. That's what V, the electric potential, is telling us. So if it's 100 joules per coulomb and I stick 2 coulombs there, how many joules of energy do you think it's going to have? It'll have 200. And that's the key. That's why we care about electric potential, because it lets us find electric potential energy. Either PE, sometimes people write electric potential energy as U. So the formula is just Q. You take the Q that you stick at that point in space. In this case, it was 2 coulombs. Take whatever Q there is, multiply it by the value of the electric potential, and that tells you how many joules there will be for the charges in that region. So this electric potential energy is between these two charges here, the charge that created the V and the charge that you stick at that point. And the V is a quick way to figure out how much potential energy, electrical potential energy, there would be. So in other words, in this case, since I had 2 coulombs there, I'd take my 2 coulombs and I'd multiply by 100 joules per coulomb, because that's the V value, and I'd get that there are 200 joules of potential energy now stored between these charges. So that's why we care about electric potential V. It's a way to figure out the electric potential energy for a charge that's placed at that point in space that has that V value. But how do you get this V value? If I hadn't given you the 100 joules per coulomb, we wouldn't have been able to figure this out. We need a way to figure out the V value at points in space based on the charges creating them, because charges create the V value. There's a formula for it. And the formula says that the V, the electric potential, created by a point charge is equal to K. K is the electric constant, 9 times 10 to the 9th, and it has units of Newton meter squared per coulomb squared. So that's always K. You take that K and you multiply by the charge that's creating the V value. So in this case, it's this Q. this positive Q here, whatever Q it is, creating the V value that you want to find. And that's key. If you plug in 5 coulombs here, you're finding the V created by that 5 coulombs. If you plug in -3 coulombs, you're finding the V created by the -3 coulombs. Sometimes there's problems with multiple charges in it, like this one. And this Q has got to be the charge creating this V. Not the charge you placed at that point in space. I don't put the 2 coulombs up here. I put the charge creating the V value that I want to find. And then you divide by the distance. So I divide by the distance between this charge and the point in space that I want to figure out the V value at. Some people call this the radius. I don't like calling it the radius. It makes it sound like there has to be a circle. There doesn't really have to be a circle. This R would be the distance from this point of charge creating this V value to the point in space where I want to determine the V value. That's R. So this is R. So how would we determine this? Well, let me just give you some numbers. Let's say the charge we stuck here was 1 nanocoulomb. Nano is 10 to the -9th. So let's say that was 1 nanocoulomb. And let's say the distance from this charge to this point in space was, let's say it was 9 centimeters. And I want to know, what's the V value? Well, I can solve for it now. We've got our formula. The V would equal, all right, my K is 9 always, times 10 to the 9th. And it's newtons meters squared per coulomb squared. And then I multiply by my charge. And I told you that the charge here was 10 to the -9th coulombs. This is a 9. And my distance, I divide by the R value, and the R value is 9 centimeters, but be careful, everything's got to be in terms of meters, kilograms, and seconds when you're doing physics with constants. Look at this, is in terms of meters. So I've got to use meters here. So 9 centimeters is 0.09 meters. And if I multiply all this out, what you'll get, this 10 to the -9th cancels this 10 to the 9th. By powers of 10, these just go away. And then I have 9 divided by 0.09. That's going to equal 100. So I chose this so that we got the same answer down there. Get 100 joules per coulomb. You might be like, where'd the joules come from? And how's this joules per coulomb? Well, let's look at it. If we took, look at, one of these meters cancels one of these meters, and one of these coulombs cancels one of those coulombs. What are we left with? We're left with Newton times meter over coulomb. But Newton times meter, that's force times distance, that's joules. That's where we get joules per coulomb. So this really does give us the number of joules there will be at a point in space per coulomb of charge that you put there. And it works for any point. You pick any point. If I picked a point twice as close, that's half as far away, say some point over here. Let's say this R value here was only 4.5 centimeters. Well, I'm dividing this by R. So if the R is half as big, this point over here would have a V value of 200 joules per coulomb. And the closer I get, if I went even closer, if I went to a point that was 3 centimeters away, well, this is a third as much as this other distance. So if I'm only dividing by a third as much distance, I should get 3 times the result. This R is not squared, it's just R. So this point would have a V value of 300 joules per coulomb. This tells me if I wanted to get a charge to have a whole bunch of potential energy, I should put that thing nearby. I should stick it over here. This would give me a lot of potential energy. Not quite as much. Even less. The farther I put my charge, the less potential energy it would have. There will be no potential energy until there is a charge. There will just be electric potential. But once you place another charge in that region to go with the first one, then you'll have electric potential energy, and this would be a way to find it. Q times the V that you get out of this calculation. You've got to be careful, though. Sometimes people get sloppy, and V looks, we use V for electric potential, and we use V for voltage. What's the difference? Are they the same? Not quite. Sometimes you can treat them as the same and you don't get into trouble, but sometimes you do. It messes you up. Voltage is a technically a change in electric potential between 2 points. This is the difference in electric potential between 2 points in space. So it's got the same units, because a change in electric potential is still going to have units of joule per coulomb. It's just when it's a change in, we give this a new title. We call the joule per coulomb unit a volt. So joules per coulomb are volts, but the word voltage specifically refers to a difference in electric potential. What am I talking about? Well, look at this point's 300 joules per coulomb. This point over here, 100 joule per coulomb. So the delta V, if I were to take delta V between these 2 points right here, and I asked what's the difference in V? Well, the difference in V is 200. 200 joules per coulomb. That means the voltage between those 2 points in space is 200 volts. That's what we mean. So when you're talking about a difference in electric potential between 2 points in space, we call it a voltage. When you're talking about just the electric potential value at 1 point in space, we call it the electric potential. And that's how they're related.